Hey everybody, this is a third video on section 2.6 rational functions, and I'm just going to work a few, I'm going to try anyway to work a couple of these applications of rational functions. I'm going to try to do two. So problem 70, which is on page 176 in your textbook, it says a 1,000 liter tank contains 50 liters of a 25% brine solution. You add X liters of a 75% brine solution to the tank. A, show that the concentration C, the proportion of brine to total solution in the final mixture, is this. All right, so we got two things here. We've got total solution, and then brine is just salt, right? So, and then the amount of salt. So this is a ratio of salt to solution. And if we do this correctly, we should get this equation. All right, so let's see if we can figure this out. Move this over here. All right, so let's see, there's a 1,000 liter tank, and it only has 50 liters in it, right? So, and then you're going to add X liters of something else. So total solution is 50 plus what you add later X. Right? That's the amount of liquid you add to the 1,000 liter tank. All right, what about the salt? Well, it contains 50 liters of a 25% brine solution, which means 25% of this 50 liters is salt. So I'm just going to write it as salt. For the salt, it's 25% of the 50, right? And then plus, you're adding another X liters, and this time 75% of it is salt. So that would be 0.75x. Right? Okay, so now we've got the total amount of solution, and the total amount of salt is just a percent of each part of the solution. So if I want to show the concentration, it should be the salt over the solution, right? So the concentration should equal salt divided by solution. Does that make sense? So just a ratio. So that would be 0.25 times 50 plus 0.75 x divided by the solution, which is 50 over x. I mean 50 plus x. All right, and then from that we should be able to get to here. So let me get rid of these decimals. So what is 0.25 of 50? So that's 12.5. Maybe I'll just leave it. Yeah, I see this 3/4, which reminds me of 75%. So how about this? I'm just trying to make this look the same as this. And I'm going to get rid of the decimals. So this would be 1/4 times 50 plus 3/4 x over 50 plus x. All right, I'm going to expand this. All right. I guess I need to see it. Let's see. I could How about if we just make this up here one fraction? So this would be 50 over 4 plus 3x over 4, right? And then you can, so I wrote the top as a, well, let me add one more step. All right, and now I'm going to write this as one fraction. So this is 50 plus 3x over 4. That's the top. And this I'm going to put over 1 and flip it. So I'm going to flip it and multiply. So 1 over 50 plus x. And now it looks right, doesn't it? I just got to, right here I've got, as you can see, I've got 50 plus 3x. This is 3x plus 50, so I can turn that around. I want to multiply that by 1, so that's 3x plus 50. And then here, I could just multiply 4 to that. 4 times 50 plus x. All right, so looks good. I figured out the function for the concentration based on x, which is the amount, an unknown amount of solution that's added. That's 75% brine. Okay. Here then it says determine the domain of the function based on the physical constraints of the problem. All right. So common sense tells me it's a 1,000-liter tank and you've already got 50 liters in there. So if x is the amount you add, right? You add x liters, how much can you add? Well, the most you can add is 950 liters, right? And the least you could add is 0. So that means for, this is, I guess, part A here. Part B, x has to be less than or equal to 950, but greater than or equal to 0. All right, so that's the common sense restrictions on the amount of solution you can add to this 1,000-liter tank, right? Because it's already got 50 liters to start, so that gives you 950 more that you could add. That's B. C, sketch a graph of the concentration function. Okay, so here's the concentration function. And I'll try to do this without using a graphing utility. I'll just check with a graphing utility. So I'm going to change the way this looks a little bit here. So I've got part C, I've got this function, we'll call it C of x is equal to 3x plus 50. And I'm going to distribute that 4, and I'm going to put that x first. So it's 4x plus 200, right? Okay, and we know that x can't be less than 0, so we don't have to worry about what makes the denominator 0, because nothing will, right? Because the smallest number I can really input here is 0, so that's going to give us a minimum of 200 right there, for the denominator, I mean. So I don't have to worry about vertical asymptotes and all that. Let's see. I do know there is a horizontal asymptote, though, because this is x to the 1 and this is x to the 1. And remember, when these are the same, then the horizontal asymptote is just the ratio of these lead coefficients, so 3/4. So I know when I draw my graph, if this is like 50% solution, this is 100% solution, then 3/4 is 0.75, right? So that means at 0.75, there's like a ceiling here. The solution can't go, higher than that. It can't go more than 75% salt. Which makes sense because, you had, remember, 50 liters at 25% salt, and then X is a 75% solution. So the more of this you add, the closer to 75% this is going to get. I hope that makes sense. Now, it does have a minimum, right? So if I put the minimum in, let's see, 0, then that's going to give me just this over this, right? Because if you put 0 in for here and here, you just get 50 over 200, which is the same as what? 1/4. So 0.25, and that makes sense because you start off with a 25% solution. And if you don't add any of this, then you have a 25% solution, right? So 25% is the minimum. What about if you add the max in there? Let's see what happens. So if I put 950 in, that's 3 times 950 plus 50 over 4 times 950 plus 200. Let's see what that gives us. Should be less than 75%. 3 times 950 plus 50. Oh, I should have put all that in parentheses. I'll just hit enter. And then, so that's 2,900 divided by 4 times 950 plus 200. That's 4,000. So 2,900 divided by 4,000. 72.5%. So that's like pretty close here. So if I go, let's say that's 100, I can go up to 950. There's 100, 200, 300, 400, 500, 600, 700, 800, 900, 1,000. 950 is like right about here. So when I get here, it'll be really close to 0.75. It's 0.725. So that's I'm approximating that number right there. 0.725. That right looks like right there. That's 1,000 at 950 for X. This is X. And this is the concentration, which is a function of X. C of X. All right, so what about, let's do another point. What about 500? So if I stick 500 in there, that's 3 times 500 plus 50 over 4 times 500 plus 200. So what's that? 1,500, so that's 1,550. And that's 2,000, so that's 2,200. So let's see. 1,550 divided by 2,200. About 70%. So when you're at 500, you're up here around 70%, which is... So I think it's going to do something like this. And really, the problem has to stop there because it's a 1,000-liter tank and you can't fill it up past that. So it's restricted between here and here. So that should be the graph. Let's see if that's right. So let's see. C of X equals 3x plus 50 divided by 4x plus 200. So let's change our domain. So X minimum is 0. X max, I'll just put 1,000 for X max. And we'll step that up by hundreds, I guess. The y-axis, I'll just drop it down to 0 to begin. And go all the way up to, let's just go up to 1, like I have here. So 1. And we'll mark that by 0.25. Just kind of the way I did it here, 0.25, 0.5, 0.75, right? So let's see if that works. There it is. All right, so at 500, there's 100, 200, 300, 400, 500. As you can see, we're at about 70%. And then when we get over here to 900, we're at 72.3, and then 950, 0.725. So that's it. All right, so that's one example of an application of these. There are many other types of applications. I'm going to do one more. So the next one I'm going to do is 72. Let me get rid of that. All right, it's kind of hard to read. Let's see. A rectangular page is designed to contain 64 square inches of print. The margins at the top and bottom of the page are each 1 inch deep. The margins on each side are 1.5 inches wide. What should the dimensions of the page be so that the least amount of paper is used? All right, so let's take a look at what this is all about. So you have this piece of paper, and we don't know what the shape is, because the question is what shape should it be so that you don't use too much paper. You use the least amount of paper possible, right? So let's say your paper looks like this. And you know, there's a border around the paper, like a picture frame, kind of. And this is where the words are written here, right? And this is supposed to be 64 inches squared right here. Right, so a rectangular page is designed to contain 64 square inches of print. The margins at the top and the bottom are 1 inch. So this is 1 inch, and this is 1 inch. And it says the margins on each side are 1.5. So this is 1.5 inches, 1.5 inches. What should the dimensions of the page be so that the least amount of paper is used? Okay. So I'm going to let this be length and width. And if I do it that way, then what I want to do is I want to use this idea that this inside part, which is where the print goes, has to be 64 square inches. So how wide is it here to here? And how long is it from here to here? The reason I need that is because I want to use that 64. Because I need to write the length as a function of the width. All right, so what I'm going to do is I'm going to say the distance from here to here is W, take away 2, right? Top and bottom. So this is W, take away 2. And this dimension is L, take away 3. And I know when I multiply those, I have to get 64, right? So basically, I'm calling this inside part L minus 3, and this inside part W minus 2. And when you multiply those, you got to get 64 because that's the area. All right, now overall, you know, the area of this whole piece of paper, which is what we're interested in, is length times width. So what I need to do is I've got two variables here, L and W. I need one variable. So I'm going to solve this for either L or W. It really doesn't make a difference, whichever one you want to do. So I'll just solve it for W. So W minus 2 is equal to 64 divided by that, right? 64 divided by L minus 3. And then I can just add 2 over there. So W is equal to 64 over L minus 3 plus 2. Okay, so now I've got an expression for W. Right? So what I could do, in the expression for W is now in terms of L, isn't it? So I'm going to replace that W with this expression. So the area of the whole sheet of paper is equal to the length times the width, which is 64 over L minus 3 plus 2. All right, so I'm looking for what values are going to minimize how big this paper needs to be and keep that 64 square inches of print in the middle. All right. So I could multiply this out, or I could just graph it, right? So if we try to make this look more like what we're used to, I could just multiply. I would have to multiply L to both of these, wouldn't I? So I'd have to have 64L over L minus 3 plus 2L. And that's still not one rational fraction, is it? I can put that over 1. And then what I guess I can't cancel these L's, by the way, because this is L minus 3, and that's just an L. So you cannot cancel these. But what I could do is multiply this by L minus 3 and this by L minus 3. So that gives me 64L over L minus 3 plus, let me distribute this, that's 2L squared minus 6L over L minus 3. Okay, now it's starting to look like something we're used to. And now I've got a common denominator, so I can just make it one big fraction. I'll put this one first because that's the highest coefficient. So that's 2L squared, and then 64L, take away 6L is what, 58L over L minus 3. All right. Now the simplest way to solve this, I don't think I need to do any of that. I could just graph this and look for the minimum for L. So I think I'm going to do that, but I'm also going to graph this to make sure that I did all my math correctly there. So let's see. So this is, I'll just call it A of X. I'm going to use X instead of L. Is equal to X times 64 over X minus 3 plus 2. All right, and then I'll just hit this home button, see what this looks like. Zoom out a little bit. Oh, there we go. So right here, that X value right there, 12.8, is your minimum length, right? So in other words, this, at minimum, if you want to minimize this sheet of paper, you need to make this 12.8 inches. Does that make sense? 12.8 inches right there. And I got that off the graph. So we know L, it has to be about 12.8. All right, well, what about W? Well, to get W, I'm going to have to plug L in right here, right? So the W, the width, is going to be 64 over L, which we just said is 12.8, minus 3, plus 2. So let's see what this gives us. 64 divided by 12.8, take away 3, plus 2. About 8.5. So the dimensions are 12.8 by 8.5. And that's going to give us the smallest sheet of paper with these margins that can contain 64 square inches of print in the middle. Okay, so I was going to check this to see, just out of curiosity, is this the same graph? So let's try it. Okay, let's call it something else. We'll call it b of x equals parentheses 2x squared plus 58x divided by x minus 3. And they match up, as you can see right here, right? So if I get rid of that, bring this down. So if I turn this red function off, you see it's the black. So they are the same. All right, and that's it. That's the lesson for today. I appreciate you guys watching.